Assalamualaikum warahmatullahi wabarakatuh, and good morning to all. My name is Nur Afia binti Mazlan, A167538 from set 1. Here I want to show you the simulation project of non-isothermal CSTR. So we first start with the transfer function first, which here is the transfer function. We need to calculate it, each of it, and then so by determining the transfer function we can get the block diagram. So we make it as a subsystem. So the first step is we need to do the servo control system. When we set up the block diagram, when we want to compute the P controller, this is the parameter P, I, and D, and we need to set up each for here at the proportional, integral, and derivative respectively. So for this one, this is the graph which compare the P is the green color, and the PI controller is the purple color, and the blue one is the PID controller. And this is for the servo. And next we go to the regulatory control system, which it involves a disturbance, which is load here, and same goes to the servo, but the difference is there is a load insert here. So the parameter is as shown in the table here. So the result that we get is same as before, which the green color indicate the P controller, the purple color PI controller, and of course the blue color is PID controller, which it's deviate close to the set point. Alright, this is for the single unit. So we want to go to the multiple unit. Multiple set point and disturbance. So first, this one, servo control system, but with the multiple set point. So here we can see there is the green color is the set point. For the results that we get is there is 3 verge of set point 2, and also like usual the green color indicates the PI controller, the P controller, the purple color is PI controller, and the blue one is the PID controller, which shows the best performance of it. And we need to set the point, the set time, and the final value with increasing number. And so we go to the regulatory control system with multiple. So as we can see here, there we insert another two loads that make it 3. So 3 set point and 3 load, which also with the increasing value of set point. And then so here is the result of the regulatory control system with multiple set point and multiple loads. The blue one, which is the PID controller, shows the best performance. And now this is for the Ziegler-Nichols method, which is one of the tuning method. So we need to try and error to get the gain here, and the value that I want is 1727, which shows the results here. So we can determine the time and value here as we get the this graph. And so by getting the gain value, we can continue to find the Kc, tau I, and Td. So we can insert the value of Kc, tau I, and Td by here the gain. This is the integral gain and then the derivative gain. So as we can see, all the values are different. So after we run, we can get this graph, which the green one P controller, the purple one is PI controller, and the blue one is PID controller. This is for the Ziegler-Nichols method. And the last one is the Cohen-Kuhn method, tuning method. As I can show here is the open loop block diagram. So by getting this, we can get this graph, and we need to calculate the slope, so we can get the Kc, tau I, and Td based on that. And then from that we sketch the other one with the parameter. We insert the parameter, which also has the different value of each component, and then it shows the data that we get. We can compute it. We can see here which is the perfect graph compared to Ziegler-Nichols tuning method. And so we can conclude here there is no oscillation for all of the controller, and also the settling time is short, and there is no overshoot and offset. So yeah, as you can see from all the control system, from servo, regulatory, multiple set point with servo and regulatory, and also when we compare the tuning method from Ziegler-Nichols and Cohen-Kuhn shows the best performance of it. And that's all from me. Thank you.